Okay, so for the lecture today we are going to talk about the concept of closure. Then that's going to lead us to some major ideas for this section 3.4. Here in section 3.4 we are going to talk about subspaces. Then we are going to talk about span, and then we are going to talk about null space. So, concept of closure, quickly refreshing our memory. The idea was if you have a set and you can add elements of the set, you can ask yourself, if I add them together, would the results still stay inside of that set? Simple example is like if you take a set of odd numbers, you add two odd numbers, what do you get? You get an even number. So the result is not in the set that you started with. So if you have a set and you have certain operation in mind, you act on the elements of that set with that operation. One basic question is, once you do that, have you left the set or are you still in the set? Typically we have two operations. Minimum we have two operations. We have addition and multiplication. So we have a set S and we have two operations. One is addition, and typically we have some sort of a multiplication as well. We could have other operations actually. The idea of a closure is once you perform these operations on the set that you have, would the results still stay in the set, or would you have a chance of leaving the set? If you always stay in the set S, we say the set has a closure property. If you leave, you say the set doesn't have closure property. Now, for our purposes, the set S that we are looking at is a set of vectors. It could have been a set of anything, but what we are interested is in linear algebra we are interested in vectors. Operations that we are considering, this is additions of two vectors. The multiplication that we have, of course, is a scalar multiplication. So what do we mean by scalar multiplication? Means taking a number and multiplying by a vector. So here addition meant like you have a vector v1 and another vector v2. That was what was meant by the addition. And the multiplication here, it means like you have some vector v, perhaps you are doubling it, perhaps you are tripling it, perhaps you are multiplying it by some number, say radical 2v and such. So scalar multiplication means you are taking a scalar number, any ordinary number, and you are multiplying it with the element of a vector, in a vector. The question in either of these cases, the closure question is, if you do these kind of things, do you have a chance of producing something that wasn't in the original set, or is it that always you are staying within the set that you started with? Let's take a few examples and make this thing clear. Suppose we have a set S, and that is set of set of all points or set of all vectors, if you wish, in the first quadrant. What do you mean by quadrant? So we have our standard coordinate system, and then we are focusing on all the vectors who happen to be in the first quadrant, meaning all of these type of vectors. So set of all vectors in the first quadrant, all this green region. Now, if I take two of such vectors and add them, do I still stay inside of the green region? Is that right? If I take two of these, like here, take one of them and here take another one. If I have two vectors that are in the first quadrant and then I add them, when I add them, where do I go? I stay inside of, so the vectors that are seated in the first quadrant are closed. We can say S is closed with respect to addition. That's just a vector addition. How about with respect to scalar multiplication? Well, scalar multiplication, you have to keep in mind that sometimes you are multiplying with a positive number, sometimes with negative numbers. So these are, unless they are ruled out, you have to consider all of such things. If I take any of these vectors in the first quadrant and I double or triple it, would it stay inside the first quadrant? Well, yes. It's not a big surprise. You double it, you triple it, whatever you multiply it with is still in the first quadrant. But if you multiply with a negative number, what happens? It goes into the third quadrant. So if you insist that your original set has to sit in the first quadrant and you expect to play with both positive and negative numbers, then those negative numbers are going to give you a headache that once you operate with those, you are going to leave the original set and your set is no longer closed under multiplication. So we can say S is not closed with respect to scalar multiplication. Or sometimes they just say multiplication because the assumption is that that is all that we are caring about. That's the only thing that makes sense here. Now, what kind of a set can you consider from beginning that would be closed with respect to both of these operations? What should I do as a starting point such that with respect to both, would this thing do it if I have, well, somebody might say, well, okay, let's consider both of these. Meaning what? Meaning all vectors, what does that mean? All vectors that either go here or go here. Would that be the set of this new green set or the new yellow set, if you wish? Is that closed with respect to multiplication? So let's consider this set, say, call it Q. It's cool. So question is Q closed with respect to, again, we're just simplifying this thing with respect to multiplication, meaning scalar multiplication. What is your answer? Yes, that is. If I double any of these things, well, stay here. If I double these guys, stay inside this yellow region. If I take one of these things, multiply by negative, it just simply goes to the other side. So if I had some vector here, some vector v, I multiplied it by minus 2v. Well, minus 2v is on this side. I am on the safe side. Now, the question is, how about the other one? Is Q closed with respect to addition? What's wrong with it? With third quadrant. you could end up somewhere else. Yeah, we fixed one side, but the other side got damaged. So if you have some vector here and some vector here, you add these two, you end up being somewhere here. So, and that wasn't part of the game to begin with. So we fixed some side and the other one suffered. So the answer is no. So as an explanation, if you add a vector from first quadrant to a certain vector you could end up in a second quadrant. You don't have to, but it's possible for that to happen. And since that's a possibility, we say the answer is no. It's not definite that it will be closed. What is important for us is to isolate those sets where both of these two properties are satisfied. Both closure properties are satisfied. If that is so, what we are dealing with is an important topic, and we are going to call that a subspace. So we are going to have a definition of a subspace. So we are going to be clear on what we mean here. Originally, we start with some vector space. It could be one-dimensional, two-dimensional, three-dimensional, or whatever number of dimensional space that you start with. So this is your original space, which is having some vector properties. We said there are a bunch of vectors there. You can add them, you can multiply them with scalars and such. So we always have a notion of one gigantic vector space in mind. Then we take a chunk of that space. Let me limit myself to the two-dimensional situations where pictures are easy. So a vector space in this case would be the set of all vectors that are seated here. So anything goes, that's going to be our original vector space. Now we are taking subsets of this. That is, we are looking at a particular group of vectors that are seated here. So I could have, for example, just the vectors whose tips end up here. That means I could have like just these vectors. Okay, these red vectors. This is going to be a subset. Subset is just same notion of subset you had in middle school, high school. You have a big set, and then a chunk of it would be a subset. Subsets of this type might be important in calculus or somewhere else, but right now they don't play much of a role for us. We are going to limit our attention to particular type of subsets. So we will look at particular type of subsets. These are sets which are closed under vector addition and scalar multiplication. let's see. Let's isolate these things. Let's see who are they. Again, we're just limiting ourselves to 2 dimensions so that it's going to be easy to draw. This original set, which is containing all the vectors in it, okay, that set of the entire set of vectors, that itself is one such thing. This, the set of all vectors, of course they are closed under vector addition. If you add 2 of these green ones, you're just going to get another green one. Is that right? If you multiply any of these green vectors with any number, you're just going to get another one of this group. So the set of all vectors that were there, the original vector space, is going to be one candidate for what we are after here. What else could be the shape of that set of vectors that satisfy these 2 properties? We just saw some examples. So tell me a particular subset of these green vectors such that if I add 2 of them, I'm still inside of the original set. And if I pick any of them and multiply by any number, I'm still inside of my starting set. Can you describe what chunk of these vectors should I consider such that it's closed with respect to both of these 2 properties? Say it again. All but one? Okay, all of them, yes. All of them, yes. All of them have these 2 properties. The question is there anything else other than targeting all of these? Is there, if you wish, a thinner set? Something not as crowded as this, small chunk of it, which still has these 2 properties. Let me draw some example. Would this one consider all vectors that are lying down here? Would these vectors have the property of closure under vector addition? If I have 2 of these vectors that are lying down here, if I add them, what do I get? Another one that is still lying down here. Is that right? If I take any of these vectors, multiply by, say, 2, 3, pi, e, minus 5, or anything, would they ever have the chance of leaving the x-axis and go somewhere else? No. You double it, you're still on the x-axis. You triple it, you're still on the x-axis. So this is one particular subset. It's not the whole thing. It's not the whole thing, but still has both of these properties. Can you think of other subsets which have, you say what? Go up instead of going horizontal. All of these guys, that's another example of a subset that has both closure properties. Anything else? Anything? Exactly. Now let me ask you, would any straight line do, or is it a particular type of straight line that we want? Exactly. Yeah. Excellent, excellent. So what we want here is, if you take this line, any line that passes through the origin, and you line up all possible vectors on that line, whatever you do with these vectors, whatever you do meaning, well, there are only 2 things you could do anyway. If you add 2 of these, you still line up here. If you multiply by a number, you still line up here. So far, if our original set is this big thing of the subsets that have these properties, one is the thing itself, which we feel it's a 2-dimensional thing. We're going to talk about dimensions later on, but right now it looks like a big thing. It's 2-dimensional. Or we have this collection of 1-dimensional objects. All of them have this property. So what objects are these? These are lines through origin. Each of them individually is going to have that property. Let me make sure you follow the conversation here. Would it be okay? Could I sell you this one as a set with closure property? Can I consider all of these with all of those? No, at the same time, no. You can't have, this set doesn't have closure property because perhaps one of these wants to join up with one of those. As soon as you add them, you have left the original set and you are entering uncharted territory here. That wasn't part of the original game. So this is, this does not have, is not closed under addition. Okay, so this is out there. This wasn't acceptable. These are a single line that goes to the origin is a particular subset which has these closure properties. We are going to call these guys subspaces. This is a subspace, that's a subspace, that's a subspace. That whole thing is a subspace. Any other subspace you can consider. Remember, we started with a very thick item here. Here we have kind of a thin one. What would be an item that is even thinner than this and still has these properties?
Origin itself.
Excellent. Origin itself. Just that single dot there. Well, it's just a zero vector. Whatever you do to the zero vector is still a zero item. You haven't left what you started with. So a zero vector is kind of a trivial subspace. That's also a trivial subspace. Throw everything in the bag. Yes, you have the property because you had it from the beginning. Just keep the origin. Yes, that's a subspace. And these are things in between. So these are example of subspaces. We kind of sense that this is two-dimensional, this is one-dimensional items, this is a zero-dimensional item. Now, pictures in higher dimensions is going to become complicated, but ideas are essentially the same in 3 dimensions. So the question is, what are possible subspaces of the 3-dimensional space? Three-dimensional space, you call it R3. That's just what you see like in calculus or something. Or just imagine this room with those lines in the corners also extending to the room next door, or upstairs and downstairs, so you have negative components as well. Okay, what are the subspaces? Subspace is a subset that has closure property. Well, what are the subspaces? We learned first of all the thing itself, the whole thing, whatever you started with. That's a kind of a cheap shot. What was the other cheap shot? The origin. So to the origin itself. Now the other ones we are going to just talk it with words and or pictures and clarify it later on. So what do you think is the other item that is in this list? Let me list this thing for item. Any straight line but we said not any straight line. I couldn't have it all the way up here. What should be true about it? It has to pass through 0, through origin. So what do we mean? Like this x-axis, y-axis, or it doesn't have to be an axis. Any of these lines that go through origin, these are legitimate answers. What else? Let's see. That picture got crowded. Let's. What else can you imagine that if you limit yourself to that entity and you do these vector operation, addition or multiplication, you still stay inside of whatever you started with? Yeah, excellent. Let's start with an easy plane. Like if I start with like this XY plane here. Is that right? If I have one vector here and another vector here, if I add them, if two vectors that I had to begin with were on the XY plane, if I add them, what happens? You end up wherever you were. You're still on the XY plane. Neither of these original vectors had any elevations. So when you add them, you don't gain any elevation. If you multiply by a number, like if you double it, the original vector wasn't taking off. When you double it, you're still not taking off. You multiply by -1 and so on. So this is an example. This would be XY plane. Of course, you can imagine that the XZ plane, the YZ plane, they are also subspaces. Well, you don't have to be any one of these nice planes. You could be just any plane, so long as we had one important restriction. What should be true? It should pass through the origin. So here is why pass through origin? Because, well, if you're not passing through origin, if you add two such, imagine, let's see, in 2 dimensions it's easier to show. If you have a line that doesn't pass through origin, you take two vectors that are ending up on these lines, on this line, you add them, you get out of the line. Same issue shows up with respect to planes. If your plane didn't pass through the origin, you add two vectors that ending up on that, the sum is going to leave the, so any now many of the questions that you face in this section are kind of not picture driven, rather they are defined by a set or equations and such. Let's emphasize problems from say 1 through 24. Do as many of these things as it takes until you get the hang of this. So the way it goes is that these problems are set by first giving you this is from section 3.4, page 176. Question? Let's pick some of these things just for practice. First, the book gives you the idea of what is the big picture, what is the starting set that we are picking things out of. So typically there are R2, R3 or something. Okay, and then there is a subset. Some subset is given. For example, here it says consider set of as a subset of R2 of points that are of this look or this shape. S and 2S is referring to a point or to a vector whose first component is something and whose second component is double of the first one. And then it says S is just a real number. Question that the book is asking is S closed under addition? How about scalar multiplication? And then finally, is S a subspace okay, all the 24 questions have this kind of a format. So who is this? This is like a grandfather set or something. That's like a set of all points you have. Okay, this is your original V. Everything goes. On that set, you are picking up points whose coordinates act like this or look like this, S and 2S. Tell me something about these points. Like, for example, if S is 1, the point that we are looking at is the point with coordinate 1 and 2. Is that right? If S is 2, that's going to be a point with coordinate 2 and 4. Well, S doesn't have to be a whole number. S could be a half. I'll be here. S could be 0. S could be minus 1, and so on. And somebody said the set S constitutes what kind of a shape? If I consider all of these, let me correct this. And this was just so you have to realize that this set S that it is talking about in this style is actually a straight line. You can see it's a slope 2 and passes through the origin. Is S closed under addition? Yes. Is S closed under scalar multiplication? So what does that mean? It means addition, like if I take two of these things and add them, do I stay on the green region? Yes. If I take any one of them and double or triple multiply by minus 1, do I still stay here? Answer is yes. Is it going to be a subspace? This answer is yes if those two are yeses. If any of them is a no, this is going to be a no. So a subspace is an entity that answers in positive to both of these two questions. Now, sometimes we are going to do these things with just algebra. Sometimes these pictures are not easy to draw or just take too long and not all that helpful. So what is meant by this? Let's take one element of this. I taken one element of it like x and 2x. And let's pick another element of it. And that other element of it would be y, for example, and 2y. So I'm picking one point here, x and 2x, that could be, say, here, and another one, y and 2y, could be here. The question is, under addition, do I stay inside of the set? Well, let's do addition, see what happens. Add these things for me and tell me what we get. What's the first component? X plus y. What's the second component? 2x plus 2y. What is the membership criterion? Who is it member of S? Question is this guy a member of S? How do you decide yes or no? The second component has to have what relationship to the first component? Has to be double of. If this guy has this look that his second piece is double of the first piece, then it is a member. Well, this one does have that property, because I can write the second piece of it as double of the first piece of it. So this guy, we say, is in S. This guy is in S. If we can come up with a verdict that the last guy is also, we are not just saying it, we just did algebra and say the second piece is double of the first piece, therefore it is in S. So second component is double of the first component. So the sum is in S. How about under scalar multiplication? So how do we try that? Again, I pick one representative member, like x and 2x. And I pick scalar. scalar like some number, like 2, 3, 5, 10, and I multiply. How do I multiply? Rx and 2Rx, or if you wish, R2X. So second element is twice the first element. So we started with something that was in S. And this guy is a scalar. And what I have is that this is in S because for the same reason. Second component is double of first component. So it is in S. Okay, let's pick something with a little bit more meat to it than what we just mentioned. And okay, problem 6 says V is R cubed. S is the set of triples X, Y, Z. So these are like vectors in R3 or points in R3 with the property that Z is X plus Y plus 1. Same question. Is S closed under addition? How about under multiplication? And finally, is S a subspace? Okay, we are going to go through two stages. One is your mind makes a decision before you even do conscious arithmetic. Sometimes you just give the answer in a step, and then you have to kind of present your answer in a kind of understandable way for somebody else. Why is it that you decided the way you decided? So there's a verdict, there's a proof, and that clears the case. What is your verdict here? Is S closed under addition? Yes, no, maybe? Which one of these two questions are clearer for you? Addition, multiplication? So, who says yes, who says no? So we have one answer for yes. Anybody else willing to buy into that? Maybe multiplication is easier for you guys to work with first time around. Either way, so you're a little bit reluctant. Well, in that case, what you do is that you do a few trial and errors. If any single example that you pick up fails these tests, what would you say the answer to the part C? No. So that's a kind of easy case. To disprove something by a single counterexample, you're all set. You're ready to go home. To prove that in every single case it has these properties typically takes a little bit more effort. So since we are kind of lost in is the answer yes or no, we at least go wet our feet, see what's the situation. So give me three numbers that such that this XYZ is a member of S. The numbers that you pick should have a certain property. What property should they have? Tell me. Suppose I start with 2 and 3. Who should be Z? 6. Is that right? The kind of guys who are member of this set S is in S. Why? Because the last guy is the sum of the first two plus a 1. Now, if it wants to be closed under multiplication, what should be true? Like if you double it or triple it, it still have the same format. Let's take this thing and do something to it. Say double it. Double it for me and tell me what you get. 4, 6, and 12. Is this guy member of this set? No. Is the last one sum of the first two plus 1? No. is sum of first two plus 2. What happened? Well, if you doubled x and y and a z, you need a 2 there to make the two sides equal. So this one as it is not in S, because it just doesn't subscribe to that format. So already we have an answer to C. What's our answer? No. No, because this is a proof for it. Why not? Because it's not closed under multiplication. Now, how about the answer to the first one? Give me another member of this set. Actually, that one would do too, but just for 1, 1, 3. Now, if a set wanted to be closed under addition, when I take these two and add them, what would I expect to get? Well, let's add them. Get 1 and 2 is 3. 1 and 3 is 4. 3 and 6. So this one is in S. This one is in S. I added them, and how about the outcome? Is that member of S? The last one is not sum of the first two plus an extra. You need 2 extras. So what's your answer here? No. So in the case you want to say no, you give a counterexample. You say, look at these guys. Here I took these two, added them. This one is not in S. If you wanted to be closed under addition, it had to be still in S. Okay, so that's a kind of a new notion for you guys. You haven't seen it in calculus. You need to practice. It's a very simple notion, but you need to keep working on it, regurgitating the idea until it kind of settles what is that we are talking about. If the idea looks strange to you, then try all 24 of these things. And then next time we are going to go after the null space and all of those. So good luck and God bless.